This split-screen display shows a terrifying clinical scenario. On the left, an intake form for a newborn in the NICU exhibiting severe brain edema, alternating muscle rigidity, and urine that smells distinctly like maple syrup. On the right, an automated liquid chromatography mass spectrometry readout displaying a massive abnormal chemical spike at an exact mass-to-charge ratio of 132.2. The clinical presentation points toward a catastrophic genetic block, destroying the infant's central nervous system. But that same data profile could also be the result of a subtle, easily overlooked analytical error inside the laboratory. Resolving that diagnostic split requires us to isolate a single molecule, leucine. This is an essential branched-chain amino acid. The human genome lacks the necessary enzymes to synthesize it, meaning we acquire our entire supply from our diet. Yet it accounts for roughly 10% of the physical mass of the entire human proteome. Inside a cell, leucine serves a dual purpose. It acts as a heavy load-bearing structural brick, while its physical presence floating in the intracellular fluid operates as an active site manager, broadcasting a direct anabolic signal that commands the cell to build new tissue. To solve the infant's emergency, we have to map exactly how this chemical behaves. We need to track its hydrophobic physics, trace its systemic transport network, identify its highly toxic pathological failure modes, and navigate the analytical traps laboratories face when trying to measure it. Ultimately, surviving this metabolic crisis depends entirely on understanding how human biology translates a specific dietary molecule into systemic structural growth. We start with the physical architecture. Leucine consists of a long carbon chain with a highly specific structural quirk, a branch sprouting at the gamma carbon position. This specific configuration gives leucine an intensely hydrophobic isobutyl side chain. It absolutely repels water. In the fluid environments of a cell, newly forming proteins are assembled in water. Because leucine side chains cannot tolerate this moisture, they trigger a hydrophobic collapse. They panic, forcefully clumping together and diving deep into the central core of the protein. As they squeeze inward, they physically expel the structured water molecules that were trapped inside the folding chain. Ejecting those water molecules increases the overall entropy, or disorder, of the surrounding fluid. That sudden burst of thermodynamic energy is exactly what the system needs to permanently lock the protein into its final, rigid, three-dimensional shape. That water-repelling thermodynamic force dictates how our physical tissue is constructed. But when leucine is not actively incorporated into a protein and instead floats freely within the cell, it behaves as a chemical trigger. As the local concentration of free leucine rises, the molecules bind directly to an intracellular receptor called cestrin-2. This interaction triggers the mTOR-1 signaling pathway. The complex moves to the lysosomal membrane, transitioning the cell from autophagic degradation to de novo protein synthesis. This growth command is not isolated to skeletal muscle. Leucine broadcasts this anabolic signal across completely different organ networks simultaneously, most notably the pancreas. Inside pancreatic beta cells, elevated leucine encounters an enzyme called glutamate dehydrogenase. Instead of fitting into the primary active site, leucine binds to the side of the enzyme. Its sheer physical bulk warps the shape of the enzyme, forcefully springing it open through allosteric activation. Forcing that enzyme open massively accelerates the production of cellular ATP. That sudden spike in energy slams the cell's potassium channels shut, alters the membrane voltage, and triggers an immediate, calcium-dependent dump of insulin into the bloodstream. Through the mechanical force of hydrophobic collapse and targeted receptor locking, leucine links dietary protein intake directly to systemic fuel storage and the assembly of new structural proteins. Because this molecule wields so much biological influence, the body distributes it using a highly specialized, guarded pathway. Normally, when you ingest amino acids, they are absorbed by the gut and routed straight to the liver for immediate chemical inspection and processing. Leucine bypasses this entirely. The human liver lacks the necessary branched-chain amino acid aminotransferase enzymes, or BCAT, required to break leucine down. This absence grants leucine a free physiological pass directly into systemic blood circulation. It travels completely unaltered straight to the peripheral tissues, allowing skeletal muscle to hoard roughly 75% of the body's entire leucine supply. Skeletal muscle claims the vast majority of the nutrient, but a small fraction must reach the central nervous system to regulate energy status. To get there, it has to cross the notoriously strict blood-brain barrier. Because leucine is bulky and hydrophobic, it cannot drift through lipid membranes. It requires a specialized active transport gateway, known as the LAT1 transporter, to pull it inside the brain. This gateway creates a severe toxicological vulnerability, often seen when fitness enthusiasts consume massive doses of pure leucine isolate powders. That unnatural bolus spikes plasma levels so rapidly that leucine competitively saturates every single slot in the LAT1 revolving door. Leucine shares this exact door with other crucial amino acids, specifically tryptophan and tyrosine. With leucine hogging the gateway, tryptophan and tyrosine are physically blocked from entering the central nervous system. This induces a sudden, localized drought of serotonin and dopamine, causing profound neurological lethargy and loss of cognitive focus. By bypassing hepatic clearance, leucine reaches muscle tissue efficiently. But that same evolutionary privilege means sudden external overloads can directly crash the chemistry of the central nervous system. A temporary chemical jam from a supplement overdose resolves once the body clears the excess. In a healthy system, skeletal muscle relies on a multi-enzyme complex called BCKDH to snip apart and burn leftover leucine for fuel. Maple syrup urine disease, or MSUD, is an autosomal recessive mutation that completely destroys this BCKDH enzyme complex. The cellular scissors vanish, halting the oxidative decarboxylation process entirely. With the primary breakdown pathway severed, leucine aggressively accumulates in the blood. Even worse, its transamination byproduct, a highly toxic keto acid called KIC, rapidly builds up alongside it. KIC operates as a potent neurotoxin. It directly attacks and disables the osmoregulatory pumps on brain cells. As those pumps fail, water floods unchecked into the cerebral tissue, driving catastrophic, life-threatening brain edema. As these toxic keto acids saturate the infant's bodily fluids, they produce a distinct, sweet, maple syrup-like odor. Without immediate intervention, the edema forces the neonate into a coma, followed by central respiratory failure. Emergency management requires extreme measures. Clinicians immediately hook the infant up to emergent hemodialysis to physically scrub the circulating leucine and KIC from the blood plasma. But the secondary intervention is entirely chemical and highly counterintuitive. The medical team aggressively infuses the infant with high-dose intravenous glucose paired with synthetic insulin. This executes the anabolic shift. By utilizing insulin to signal systemic fuel storage, clinicians force skeletal muscle cells to aggressively extract amino acids from the circulation. The muscle tissue sequesters the toxic leucine and KIC, trapping these metabolites behind the cell membrane and lowering their concentration in the blood before they can damage the central nervous system. To save an infant from a broken leucine cleanup mechanism, we weaponize the very growth signaling network leucine naturally controls. This brings us back to the NICU crisis at the start of the episode. Was the massive spike on the LC-MS-MS readout proof of MSUD or a catastrophic analytical failure? The answer hinges on a severe chemical trap. Leucine, isoleucine, and alloisoleucine are structural isomers. They are built from the exact same atoms, merely arranged in slightly different configurations. Because they share the exact same ingredients, they possess an identical molecular weight of 131.17 grams per mole. Standard mass spectrometry filters identify molecules solely by mass, rendering the machine completely blind to their physical differences. We call this the triplet trap. If a clinical laboratory utilizes a short, poorly optimized chromatography runtime to rush the test, all three isomers travel through the system and hit the detector at the exact same moment. Their signals blend together into one massive, falsely elevated peak on the readout. The mandatory resolution is physical separation. Laboratories must implement extended, high-resolution chromatography gradients. This acts as a chemical obstacle course, slowing the slightly different sheets down at distinct rates. They hit the mass detector at different times, creating distinct peaks. Only by achieving this exact temporal resolution can the pathologist isolate L-leucine. Detecting that specific isomer is the single pathognomonic marker that confirms a true genetic diagnosis of MSUD. Even with perfect chromatography, pre-analytical interferences can ruin the data. Ingesting a protein-rich meal causes a postprandial ingestion surge, artificially inflating plasma leucine levels by up to 50%. Drawing blood requires a strict 12-hour overnight fast. Furthermore, a difficult blood draw can cause mechanical hemolysis. If the needle ruptures the patient's red blood cells, their highly concentrated internal leucine pools spill directly into the plasma. The sample measures the wreckage of popped cells rather than true circulating chemistry, rendering it totally useless. Managing these isobaric complexities requires relentless laboratory quality control, strictly maintaining a tight total allowable error, the 15%, and aggressively tracking calibration deviations. In metabolic diagnostics, separating identical masses through the dimension of time is the ultimate safeguard against a fatal medical error. Measuring these kinetics demands rigorous diagnostic stewardship. Complex mass spectrometry profiling is a resource-intensive tool reserved for severe events, like neonatal encephalopathy or ICU malnutrition. Ordering this panel to investigate generalized clinical fatigue is an inappropriate use of laboratory architecture. The core rule for the clinical pathologist is absolute specificity. Clinicians must aggressively reject any laboratory result that reports a blended total BCAA or leucine isoleucine value. Blended reporting entirely masks the presence of allo-isoleucine, risking a misdiagnosis during the critical early window. The biological impact of this molecule rests on two core pillars. First, it acts as a hydrophobic structural anchor, dictating protein shape. Second, it serves as the master mTOR1 signaling switch, activating global tissue synthesis. Because it bypasses hepatic clearance, it rapidly feeds peripheral muscle. But that same route creates a dangerous competitive transport bottleneck at the blood-brain barrier, exposing the central nervous system to severe metabolic encephalopathy if cellular breakdown fails. Tracking these pathways and distinguishing genetic failures from harmless fluctuations relies entirely on pristine collection protocols and high-resolution chromatographic separation. We completely lack the ability to manufacture this critical signaling node, leaving our physical structure entirely reliant on acquiring this specific chemical geometry from our external diet. Recent findings in systems biology suggest an alternative source. Researchers are isolating specific commensal bacterial colonies within the gut microbiome, such as Bacteroides, that possess the enzymatic pathways to synthesize leucine. This identifies a potential internal supply chain that does not rely on direct protein ingestion. Until then, leucine remains a testament to the high-stakes precision of human architecture, a system designed to flawlessly translate external chemistry into the load-bearing structure that keeps us alive.